All right, it looks like we have a circular disc with a circle cut out off center, okay? And it seems like, um, yeah, it seems like we need to figure out where to set our origin 0, comma 0, right? I don't know if I gave you a hint where to set that, but I think setting it at the center of the solid disk will be beneficial for us because then we could actually get rid of one of the you know center of mass when we calculate it. Okay, so if we consider this point right here to be 0, comma 0, anywhere to the right of that would be positive x, anywhere to the left of that would be negative x, anywhere above that will be positive y, anywhere below that will be negative y. All right, and since this has symmetry along the x-axis, right? It seems like my center of mass has to be on my x-axis. And without really knowing the actual numbers, we could probably predict it's going to be somewhere on the left side of this center, right? Somewhere going. But is it going to be on the plate or is it going to be away from the plate? We don't know. We have to figure that out. All right. So first thing is first, we need to figure out what the mass of these are. So we have an uniform circular plate of radius of 2r has a circular hole of radius r cut out of it. And it's not cut out at the like right at the nice edge either. The center of the small circle is distance 0.8 r from the center of the large circle. Okay? What is the position of the center of mass of the plate? Hint, try subtraction method. All right? So I'm going to consider this solid plate has the same uniform density. So the solid plate with circle with shaded is equal to the mass of the solid over the volume of the solid, right? So if we were to work this thing out and solve for the mass of the solid circular plate is equal to rho times the volume, right? Volume, which is, let's just write down volume for now. So since the uniform density of this, right, is constant, so rho times the volume of this solid circular plate is pi r squared times the thickness d. Okay? Since the radius is 2r, you have to square that 2r, and then thickness d. All right? So if we were to rewrite this, this will be rho times pi times 4r squared d. Okay? Now if we were to take a look at the whole is basically rho whole is equal to. Now these rows are the same because they're basically made from same material, same uniform density, but that same uniform density is cut out. All right, so this rho is the same. So that is the mass of the whole divided by the volume. Right? So the mass of the whole becomes rho whole and then volume, which is pi r squared d is the volume. So this would be the mass of the hole they're going to cut out, and this will be the mass of the solid they're going to work with, right? So how do we calculate the x sub cm? Well, if we calculate the x sub cm, we're looking at just along the x-axis. That is really nothing more than, right, the mass of the solid times the x sub cm of the solid, right, minus we have the mass of the whole times the x sub cm of the whole. Whole thing divided by mass of the whole, a mass of the solid minus the mass of the whole. Okay? So all you have to do is now plug and chug. So here, it looks like the mass of the solid is basically rho pi r squared d times 4, right? This times the x sub cm for the solid is 0. Okay, 0. Minus mass of the whole, which is basically rho pi r squared d times the x sub whole is actually 0.8 r away from our origin to the right of it. So it's positive 0.8 r is my x sub cm for the whole. So 0.80 r is my, okay? So now we say, okay, and then mass of the whole, mass of the solid is 4 rho pi r squared d minus rho pi r squared d. So now we know this is going to be 0 because 0 times anything is going to be 0. So 0 minus, right? 0 minus. This right here is simply 0.8 rho pi r squared d times r. Now I did not put these r's together because you'll see why, right, later. Here I got 4 rho pi r squared d minus 1 rho pi r squared d, so I should get just 3. I should get 3 rho pi r squared d at the bottom. So this turns out to be, well, look at this, rho pi r squared d at the top and rho pi r squared d at the bottom should be able to be canceled out as 1. So only thing we have left is negative 0.8 r over 3 x hat. I forgot to put the x hat in. X hat, because we're looking at only in the x direction. So here, if I were to, divide this out with our calculator, I should get negative 0.267 r x hat. So that is the x center of mass. Well, what about the y? What about the y? Well, what's the y sub cm? Well, y sub cm is basically same thing what we did, but this time we have MO, MO, and then x solid right here, minus, right, minus M whole right? Times x, y, sorry, y. This should be y whole, and this should be y. Sorry. Right, so this should be y. All right, and then this should be m solid minus m whole. Well, we already know what the y position is for my solid. My y position is 0. So this is going to be 0 minus, what's my x position? My x position, a y position for the whole is also 0. So this is also 0. Whole thing over, right? Like 3 rho pi r squared d. And that just becomes 0 y hat. So everything's just, so it's going to be along the x-axis. All right. So here, now we have the x and the y. So our final r sub cm is equal to, right, negative 0.267 r x hat plus 0 y hat. So that is my r sub cm. And that is located, right? So if you go from here, and then if you go 0.2 to the negative direction, it's going to be right at the edge. And then 0.267 is going to be somewhere on that plate, and that looks like where the center of mass of this whole system is going to be. Right there, which is negative 0.267 R. Right? Negative 0. Yeah. My cousin just sent you an email. She wants me to talk with her. Right now? Yeah. Am I in trouble? No. Okay. All right. What we have for this problem. All right. Now, any questions? Oh, thanks. Any questions? All right. This wasn't that bad, right? You could do this, right? All right. So now let's finish the rest of this homework packet. All right. So here it says, number one, we claim that momentum is conserved. And that is correct. We do claim that. Right? Yet, most moving objects eventually slow down and stop. Well, why? Explain that. Well, usually the momentum is conserved, right, when the net external force is equal to change in momentum over change in time. If net external force is equal to 0, then change in momentum must equal to also 0. Right? That's when, this is when the momentum is conserved. However, when the net external force is not 0 and you have a friction involved, right? Then, right, the change in momentum does not equal to 0, right? So usually, the friction is the external force that's going to slow things down to a stop, right? Therefore, the friction is the external force that will stop things from moving eventually, right? So the work done by friction is going to cause it to slow down and stop eventually. So the external forces basically is what friction is. And since friction is not zero, that's why conservation momentum does not happen in that case. All right. All right. Number two. When a person jumps from a tree to the ground, I don't know why you would do that, but what happens to the momentum of the person upon striking the ground? What do you think? Well, momentum is, in this case, momentum has to be conserved, you know, because as soon as the man or the person hits the ground, collision happens, right? The collision is happening, and it comes to rest, and momentum has to be conserved during that collision, okay? Because there are no other like external forces acting on the person, okay? Theoretically, the Earth will recoil, but the recoil is so small you can't even like measure it or calculate it, okay? So, okay. Number three, when you release an inflated but untied balloon, does it fly across the room? Or why does it fly across the room? Well, if you have a balloon and you blow it up, and then you let go, what happens? Well, the gas that's going to escape from the balloon, right, is going to basically push the balloon forward. But think about the gas as like microscopic bullets being fired by the gun of the balloon. So the balloon basically recoils from that, right? All these like microscopic bullets. So think of it as conservation of momentum. Okay, it starts out at 0 when it's held tight like this. But as soon as you let go, it's releasing gas, and because it's releasing gas, it has to conserve momentum. Okay, so so sum of all momentum initial must equal to sum of all momentum final. Initially, it was 0, right? But final, when I release it, I have the mass of gas times V of gas minus, right, minus mass of balloon times the V of balloon. So when I bring this to the other side, I get the mass of the balloon times the V of balloon, right? Or maybe I should like change this to negative here and then positive here. So it's correct with the, but it doesn't matter. It still works out the same, right? Because if I bring this to the other side and flip it, I get the exact same thing. Is equal to the mass of gas times the velocity of gas. Therefore, whatever this gas is coming out at, right? The speed that gas is coming out at times the mass of the gas must equal to the momentum of the balloon itself, the mass of the balloon times the velocity of the balloon. And that's why it's going to move across the room. Okay? So the momentum of balloon must equal to the momentum of gas. Matter of fact, this is exactly how the rockets work. Rockets work exactly like this because a rocket shoots the gas or fuel or flame, and that's causing the rocket to recoil forward. Okay? All right. Number 4. It is said that in ancient times, a rich man with a bag of gold coins froze to death, stranded on the surface of a frozen lake. What a poor man. Because the ice was frictionless, he could not push himself to the shore. What could he have done to save himself had he not been so miserly? What should he have done? Zach? Here's a frozen lake, right? I guess he could have played hockey on that. And here's the old man in the middle of the frozen lake, right? And he froze to death because he had huge amount of sack of gold coins that he instead of, right, like he could have used that somehow to get out of that situation. What could he have done? Buy himself something? Sarah? Yeah, if he just pushes it and throws it. So if he would have just pushed this coin to this way, what would happen to him? He'll go the opposite way, and he would survive. And then if he was really smart, he would throw it really hard, so that coin would end up at the edge of the shore, and then he'll get to the other, and then he just walks around and picks up the gold and go home. Duh. So if he knew his physics, he would have lived and have the gold coins. You know what I mean? But he died with the gold coins instead because he didn't know his physics. Right? So now, if you ever get stuck in a frozen lake with a bag of gold coins, now you know how to survive. All right? All right. So, conservation of momentum, just like this. All right? All right. All right. Let's take a look at 35. All right. Number 5. Number 5. How can a rocket change direction when it is far out in space and it's essentially in a vacuum? Yeah, basically, people thought like, and these were like NASA engineers. They thought, well, if you're out in space and you like fire a rocket engine, there's nothing to push off of, so it's not going to do anything. So it's going to stay there. On Earth, the fire is going to like push the rocket off the Earth, so like it could go. But when you're out in space, it's vacuum, so there's nothing to push off of. Is that correct? And the answer is no, because if you fire a rocket out in space in a vacuum, because of conservation of momentum, the rocket's going to recoil. As soon as you fire in one direction, rocket's going to go in the opposite direction. So it doesn't have to have anything to push off, right? You don't need to push off of anything. So if I have a rocket, right, it's going. So we're going on a trip in our favorite rocket ship, zooming through the sky. You don't know that song? Come on. Little Einstein, right? Get on board. We're ready to explore. There's so much to find. Little Einstein. So here's a rocket. So when the flame is shot down this way, think about these flames as microscopic bullets being shot out by the rocket gun, right? So due to conservation of momentum, right, you will have rocket recoiling when the engine is fired. Okay, so right, right. So now if he wants to change direction, you have to fire like a retro rocket, like retro engine sideways. If you shoot your fuel this way, now the rocket's gonna go that way, and that's how you change direction. The rocket's gonna go this way. Okay. All right. Number 6. According to equation number 5, the longer the impact of time of an impulse, the smaller the force can be for the same momentum change. Okay? The same momentum change can happen. So if you have the force is equal to the change in momentum over change in time. Okay? So the impulse itself is equal to F times delta T. So what happens? If you decrease the time, in order to keep this same, your force has to increase, right? So dP is constant. So if change in momentum is constant, right, then as delta T increases, then force must decrease to keep this the same. Does that make sense? Right? So the smaller the force can be for the same momentum change, and hence the smaller the deformation of the object on which the force acts. Explain the basis of the value of airbags, which are intended to inflate during an automobile collision and reduce the possibility of fracture or death. So, as as car crashes, the airbag deploys, right, from the steering column, right, and the face, basically, that's the face, screaming, ah, right, right. What happens? it gives more time to come to rest because now the face is implanted in here. Right? So it takes longer time, right, to slow this face down to a stop rather than a hard surface like a dashboard, you know? So this will give more time for delta T increases, right? So the force on the face decreases. Okay? That's why airbags save lives. All right. Now what? For number seven, what do you do? It used to be common sense or common wisdom to build cars as rigid as possible to withstand collision. That was the old, right? Not so smart way of building cars. Today, though cars are designed to have crumple zones that collapses upon impact, what advantage uh, does this have? Just like the airbag, it gives longer time for car to stop, right? Because as the car crumples like an accordion, it gives longer time for car to come to rest. If you give longer time for car to come to rest, the force on the car decreases. Okay? So the crumple zone is designed to and when delta T increases, then the force decreases, right, to keep the delta P constant, right? First car company to implement this was Mercedes-Benz. They were the first ones to design cars that crumples into like an accordion when it crashes into another car because that gives more time for the occupants to come to a stop with less force. You know, very smart because if they have customers who are paying $120,000 for a car, they want them alive so they could buy another $120,000 car after an accident. Duh. That's very, very intelligent, I think. All right. All right. Number 8. Why is it easier to hit a home run from a pitched ball than from one tossed in the air by the batter? Yeah, this seems very, very like counter like intuitive. It's like, wait a minute. When you hit a pitch ball coming at you at like 90 miles per hour, is it easier to hit that off into a home run than just like tossing the ball and trying to hit it that way? You know? And you're like, well, that doesn't make any sense. How could that be? Right? Here's how. Here's pitched ball, right? Let's say the ball is coming towards the bat, right? At like, I don't know, like 90 miles per hour. We'll call it V naught. So initial velocity is V naught going that way, like 90 miles per hour. Okay? And then the ball gets hit. So this is the initial condition. And then the ball gets hit by the bat, right? and it flies off the bat going the other way at, let's say, 90 miles per hour. So my V final is negative V naught, right? Going this way, okay? So when I see the final change in momentum is equal to final momentum minus the initial momentum, which means mv final minus the mv initial. My mv final is m times negative v naught minus m times positive v naught, giving me negative 2 mv naught. So my change in momentum becomes negative 2 times mv naught. However, if I look at the tossed ball, right, initially it's just up in the air when I hit the thing, right? I'm going to toss it. When I hit it, it's virtually zero speed because it's only going up and down. There's nothing coming sideways. So the V initial is 0. And when the V final, when it's hit out this way, let's say at V final is equal to negative V naught by the bat, my change in momentum is equal to momentum final minus the momentum initial, right? My momentum final is m times negative V naught minus m times 0. So my change in momentum is just only negative mv naught. So you don't have enough change in momentum to hit it out of the park. But the one that was pitched, you got twice the momentum to hit it out of the park. That's why it's easier to hit fastballs out of the park than a very slow curveballs. You know, if you hit the fastball right, I mean that's gone. Like Jimmy Rollins he's like one of the better ones who hit those fastballs out of the parks. All right, now you see the reason why it's easier to hit. All right. Next. Number 9. Number 9. So is it possible for a body to receive a larger impulse from a small force than from a large force? And the answer is yes. Why? Since impulse is equal to F times delta T, right? If I have large time, right? If I have a large time, so if I have, let's say, small force, multiply that by large time, I will have large impulse. Correct? But if I have small time, let's say I have a little bit bigger force, I have a little bigger force than this, but I have a very small delta t, I'm going to have so yes, I can get much bigger impulse from a smaller force than bigger force. Is that okay? Does that make sense? Number 10 is sort of tricky. Number 10 says a large body and a heavy body have the same kinetic energy. So what they're saying is a light body, so 1/2 mv squared is equal to 1/2 mv squared. These two kinetic energies are the same. Which has greater momentum? So they're asking, is mv bigger than mv? So they're basically asking this question. Which one is it? Is it bigger, smaller, or equal? Right? Well, let's put some numbers in there. Let's say I have 1/2, right, times 2 kilograms times 3 squared is equal to 1/2 times um, I used the wrong color. Crap. All right. Let's say I have like 4 times v squared. Let's find out how fast this v has to be. Right? So here, this looks like 9 is equal to 2 times v squared. So what's my v for the larger one if I have, right? So here, this looks like v is equal to square root of 4.5, which is square root of 4.5. It looks like 2.12 meters per second. So if I were to put in these values back, right, I have 3 times 2, right? 2 times 3 is my momentum here. And here, it looks like I have 4 times, right, 2.12. Therefore, which one's bigger? Here, it looks like I have 6. Here, it looks like I have more than 8. So definitely, the one with bigger mass will have greater momentum. So therefore, the one with bigger mass will have greater momentum. When their kinetic energies are the same. Okay? All right. Number 11. Is it possible for an object to have momentum without having kinetic energy? Oh, come on. If you have momentum, your momentum is non-zero or bigger than 0, and your v has to be bigger than 0, then kinetic energy cannot be 0, right? So if m is greater than 0 and v is greater than 0, then kinetic energy must be greater than 0, right? So No way. Can kinetic energy, can it have kinetic energy but no momentum? If you have no momentum, right, that means your mass is zero or your V is zero. But if your V or mass is zero, then you cannot have kinetic energy either. So vice versa. So the answer is no, right? So if kinetic energy is greater than zero, the momentum cannot be zero. I mean, the mass cannot be zero and velocity cannot be zero, right? Therefore, momentum has to be bigger than zero. So the answer is no and no. Okay. All right. And at an hydroelectric power plant, water is directed at high speed against the turbine blades on an axle that turns an electric generator. Do you think the turbine blades should be designed so that water is brought to a dead stop or so that water rebounds? This is exactly the same thing as pitched baseball versus tossed baseball. So definitely when the water rebounds, you get a lot more impulse out of it. Okay? So when the water rebounds, the impulse on the blade is much, much greater. Matter of fact, one person during, like, during the gold rush, I guess, designed the water wheel so that the blades rebounded the water, so it got a lot more power out of it when you rebound the water from the water blade. Same principle. All right. Oh my God, the last page. All right, the last page. All right, here we go. The Super Bowl. Right? The Super Bowl is dropped from a height h onto the hard steel plate fixed to the earth, right? From which rebounds at very nearly to its original length. So the Super Ball is dropped to a steel plate that's fixed to the earth, and then it comes down, bounces back up almost to the same height that it came down in, right? Therefore, A, is the momentum of the ball conserved during any parts of the process? And the answer for part A is yes, right? Momentum will always be conserved, right? Energy is not conserved, but momentum is definitely conserved, okay? All right. Part B, if we consider the ball and Earth as our system, during what part? Well, we already answered that. That's during the collision, right? Part C, answer part B for piece of putty that falls and sticks to the steel plate. Still, during collision, the momentum is conserved. However, the Earth and the putty would recoil, but it's just so small, and the Earth is so massive that you won't see it. You know. Imagine instead of being a putty coming down, crashing to the Earth, imagine another planet came down and crashed to the Earth and got stuck like a putty. you would definitely see a recoil, you know. So you could always bring things to much grander scale to see how it would behave. All right, number 14. Why do you tend to lean backwards when carrying a heavy load in your arms? Well, if you carry something very heavy and you carry it straight up and down like this, let's say you carry like something really big, right? The center of mass will be somewhere located like here. And the center of mass, if the center of mass is above your, beyond your toes, guess what happens? You're going to fall. Yeah, you're going to fall. I guarantee you. All right? However, if you lean backwards, now this is obviously exaggerated here, and you carry your heavy load, right? Your center of mass is above your feet. That's really broken leg there. I'm sorry about that leg. I should I should redraw that. So that that looks really painful. So I'm gonna see if I can redraw that so it doesn't look as painful. Is that better? That looks better, right? Sorry. So here is the center of mass, and as long as your center of mass above your feet, you're not going to fall over. So it's probably better to carry it when you lean it a little bit slightly back. Okay? And we could do a little demonstration if you want. All right, Zach. Stand up against that cabinet there, right? This one right there? Yeah. Okay. Now, I want you to stand there and put your heels up against the cabinet. Like this. Yeah, like that. Now, see if you can touch your toes without bending your knees. Come on, let's see. Both hands, both hands. Oh my God, notice he twisted it. See, pull straight forward.
Yeah, I can't do that.
Why not?
Because I guess my center of mass is over my toes.
That's right. As soon as he bends forward, his center of mass will go beyond his front toes. That's when he starts to tip over. Yeah. That's why now step about like maybe 2 inches off that, and then now try to touch it. Now look at that. His butt's touching the thing, right? But his center of mass is above his toes, so that's why he's not falling. You see the difference? Mm-hmm. There you go. Physics. For people at home, I'm sorry you couldn't see that, but you should try that. All right. So what Zach did was, at first, he stood against the wall or to the cabinet, and he tried to like touch his toes, right? He tried to touch his toes, and then what happened? He fell over, right? Because as soon as his center of mass goes beyond his toes, is very unstable. Okay, so but when he stepped about like 2 inches off, his butt touched, and he just center of mass stayed above his toes and it stayed stable. All right. Why is the center of mass a 1 meter length pipe at its midpoint, whereas this is not true for your arm or your leg? Well, because of it's not uniform, you know. Just certain parts of your arms like a lot thicker than other parts of your arm, right? Your biceps and triceps are a lot thicker, so more mass, right? So it's not uniformly, made, right? So for the pipe, it's very uniform. So it's boom right there. But for arm, here's your like biceps, right? And then here's your like forearm, right? So here, notice, I'm just drawing my arm here, okay? So here, so notice, right? Right? So here, after all that steroids, it's not going to be the same uniform design. That's why you're not going to have, right, the same thing, right? And last but not least, if you were to lay down, right? So if you were to lay down on the floor, right? So here's Zach laying down on the floor, right? So here, the center of mass would be right near the floor. But if Zach is sitting down, right, then the center of mass will be up here. So notice the switch, right? Notice the shift in center of mass. Okay. Center of mass of human being is usually right around the belly button area, inside the gut. Right? That's where the center of mass would be for human beings. All right. It's slightly above your belly button, but like maybe 2 inches above your belly button. That's it. I think we're done. So now, if you can go to your school with me and take a look at your where your quiz is located. Okay. So if I could bring that here, if you could go to the current unit and then open up your chapter 7 and open up your chapter 7 test folder, and this is your center of mass quiz. For if you could print this out and then work on this quiz for the rest of the period. Okay, it shouldn't take you more than 20 minutes. All right, I'll give you the whole rest of the day if you want. For you guys, I have it printed out already for you. So if you want a hard copy, I have it. If you want to use digital copy, you don't have to have it. But, all right. So that's what we're going to do for the rest of the period. All right. I'll stop the lecture here for today.